Hi folks, welcome to the channel. Today we're going to look at a typical problem when trying to machine a narrow piece of stock on the lathe and a way to solve this problem using standoffs. The actual problem is with getting the piece to mount flat in the chuck. With a longer piece, this usually isn't an issue because there is enough material for the jaws to center the piece. But with a narrow piece, it's more difficult to get it to sit flat. When we rotate the part, it's pretty obvious it's wobbling. Now we can go back in and loosen the jaws, tap the part with a mallet, and try again. We could probably get it closer. Another way is to put some spacers like parallels or gauge blocks behind the part, push the part up against the spacers, and then remove the spacers. We're going to solve this differently by using chuck standoffs. Now I'm just a hobby machinist, and I should mention that I was inspired by the YouTuber Joe Pye, who is a real machinist. I'll link to his video where he talks about chuck standoffs. Joe has a lot of great machinist videos, so check out his channel if you're looking for machining content. Let's take a quick look at the finished standoff, and then we'll look at what it took to get there. Standoffs are simply some stock that is drilled and screwed to the chuck. The jaws are removed and the standoffs are machined flat. Here I've already machined the standoffs and I'm putting the jaws back on. Once the jaws are back on, we mount the part and use a mallet to get it seated. With the standoffs, there's virtually no wobble. Okay, let's look at the next steps. First thing we need to do is add some threaded holes to the chuck. We need to consider a couple of things before drilling. The first is there is an oiler right where one of the threaded holes should go. We want to keep the oiler, so our threaded hole will need to move over slightly. The next thing to consider is we don't want to drill through the chuck. Otherwise, chips will get in the jaw mechanism. There are many ways to approach drilling the holes in the chuck. I don't have a mill and my desktop drill press isn't that accurate, so I'm going to use a technique that has worked well for me on other projects. This technique is to 3D print a template that holds drill liners at the places where the holes go, and then uses a removable drill bushing to guide the drill. This keeps the drill perpendicular to the work and allows us to precisely position the holes. Well, more precise than manually laying out the holes, marking with a punch and drilling on the drill press anyway. Check out this approach and leave a comment if you think it's a good idea, or not. This is a bit out of sequence, but I started by taking some chuck measurements and made a little sketch of the dimensions where the jaws go. I'll use these as reference points to center the 3D printed template. Here you can see the drill liners and the drill bushing sitting on the table. That drill bushing is a 4.8 millimeter or a number 12 drill, which is the correct drill size for an M6 tap. Here I'm modeling the template in Fusion 360. This feature is part of the template that will fit down in the grooves of the chuck where the jaws sit. It'll help center and position the template. Like most Fusion 360 models, we start with a 2D sketch and then extrude it to get the 3D model. This section here is the main part of the template. These holes are the bottom of the larger drill bushing liner holes. I'm adding more holes here than necessary because I haven't yet decided on where the holes go. Like before, the sketch is extruded to make the 3D model. This last part is to create the extrusion that holds the drill liners. Finally, I export the 3D model as a mesh and then open it up in a 3D printer slicer application. The slicer chops up the model into vertical sections so the 3D printer can print it layer by layer. Since the 3D model has a feature that sticks down, I need to use scaffolding and use two different printer filaments. I'm using PETG for the main filament and HIPS for the scaffolding. Here's a bit of 3D printing footage. I had some trouble sending the print to my printer. My printer was offline because the password expired. I didn't figure it out until after filming. Oh, this printer is a Bamboo Lab X1 carbon printer.
Okay, well here's the 3D printed part. Here's where the bushings go. Like I said, I only have two of these, so I gotta put them in the holes, in two of the holes, and then drill what needs to be drilled, and then pop those out and drill the other types of holes. Okay, when you 3D print a part, this has like a base where it's not supported at all. So what you have to do is you have to 3D print it with scaffolding, and that's what this is. So this is a different material. This is HIPS. This is PETG. I'm using HIPS because it has a similar temperature than what I'm printing it at with PETG. At any rate, what it does is it prints this second color, or this second material, and it holds the base of this up until we get to this level, and then this is all PETG. So what we do is we just pull this off. Usually it comes off pretty easy. Sometimes you got to work with it a little bit, but we'll get a razor blade and clean it up. But that's about it. So you can see the overhang. Let's try this out, see how it fits. And hopefully it fit right down in there, and it does. And it's really a good fit. So we'll press in these bushings next. And right, you can see. So we'll press in the bushings. The offset hole is the one that's not aligned with this hole here, and that needs to be lined up with in order to miss the oiling port there. So this is the proper way to do this right here. I've got this sitting on some standoffs, so when I drill it, it won't tip on me. So all right. Okay, not sure whether we caught it all, but we've already drilled one of these, and depth of 14 millimeters, and we'll pick up the second one. And as I mentioned, this template and drill bushing, it within a few thousandths places the drill holes, so it's really nice. And in this case, you can take it off and put it back on, and that centers itself. But the other advantage of doing it this way is it holds the drill perpendicular to what I'm drilling. So, all right, well, here's number 2. right, let's check this for depth here. All right, perfect. Turned out perfect. All right, I got a spiral tap here. All right, we got the chuck back on the lathe. I'm gonna make the standoffs out of this hex. It looks like 1-inch hex. No, it's 7/8 hex, but it's aluminum, 6061 aluminum, and so I'll cut 3 of these off about 1 inch, and then we'll chuck them up in the lathe and flatten them. And we'll drill and countersink a hole for the M6 screws. So I'll cut 3 of these off. All right, got 3 of these. Now we'll face it off. All right. the standoffs in. Butterfingers. All right. Ooh, that's not good. Okay, good. All right.
Let's see how good we did. Let's machine both sides of the disc, deburr it, and then measure it for parallelism. I started by measuring the piece with some digital calipers, but I felt like I wasn't taking accurate measurements. Time to bring out the big guns, an accurate dial gauge on a surface plate. I went through the video and recorded the various measurements, then grabbed the min and the max and came up with a variation of 0.031 millimeter or 1.2 thousandths of an inch. The piece is parallel to within a little over a thousandths of an inch. We're going to call it a success. Thanks for watching. Take care.